Good day and welcome back for part 2 of our discussion on differentiating exponential functions. In our previous video, we reminded ourselves how we define the exponential function along with some of its basic properties. In this video, we will come up with a generic formula that will allow us to begin differentiating exponential functions. Now, when it comes to developing a new differentiation formula, our typical starting point is going to be going back to that definition of the derivative. So in this case, f prime x, the derivative, will be the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x over h. And I almost always start off with this more generic formula and then go ahead and put it in terms of our specific function f. And usually the most difficult part is just making sure we get this composition correct. And our function f is defined in such a way that f of something, whatever that something happens to be, is a raised to that something. So f of x plus h is simply a to the quantity x plus h. F of x is a to the x, and we're dividing everything by h. And we now find ourselves in a familiar position. We cannot simply substitute in h equals 0. That would cause us to divide by 0. Instead, what we can do is some amount of algebraic manipulation until we can substitute in h equals 0 or we have a familiar limit. And in this case, the algebraic manipulation is using properties of exponentials. This a to the x plus h can be broken up. We can write this as a limit as h approaches 0 of a to the x times a to the h minus a to the x all over h. And note, both of the terms in the numerator involve an a to the x. So let's go ahead and factor that a to the x out. So algebraically, we have an a to the x times the quantity a to the h minus 1 over h. And we'll even go ahead and take this a step further and make the observation that the quantity a to the x with respect to h is a constant, and we can pull constants out of a limit. That is, this becomes a to the x multiplied by the limit as h approaches 0 of a to the h minus 1 all over h. And gosh, we still cannot substitute in h equals 0, but I do want to make an observation about this limit. By comparison to our starting point, these are very similar looking limits. In fact, this limit results precisely when we substitute in x equals 0 in our original limit. So let me kind of just make a note to the side so that we can see precisely what this limit is. F prime of 0 would be the limit as h approaches 0, and I'm going to substitute in x equals 0. So this would be a to the 0 plus h minus a to the 0 over h, which can be simplified as a to the h minus 1 over h. And this limit, which represents f prime of 0, is precisely the limit that we resulted in. So this is equal to a to the x f prime of 0. And it is somewhat of an unsatisfying formula in the sense that it's not the simplest formula for us to use in general. So if we have the function a to the x, an exponential function, what we have found is that its derivative, f prime of x, is equal to a to the x times f prime of 0. But it does have a really nice form. It ends up being a to the x times f prime of 0, which is a number. And before going on to make other observations, it's worth noting that sometimes we will go through the details like we've done here to see where a formula comes from. other times we won't. I wanted to go through the details in this case because it's a good reminder of the definition of the derivative along with properties of the exponential function. But in this case, do not worry, this is not something I'll ask you to recreate later on. There is a very specific case in which this formula is extremely convenient. It turns out that the number e we introduced in our previous video can be defined in the following way. It is defined to be the single number where the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. And note, this is precisely the quantity we encountered in our previous computations. Let's go ahead and connect this together. For the function f of x equals e to the x, this limit to the left is telling us that f prime of 0 is equal to 1. So if we wanted to differentiate e to the x, its derivative would be e to the x times f prime of 0, which in that case is 1. And this leads to one of the most convenient possible differentiation formulas. E to the x is the only function for which the derivative of itself is itself. And similarly then, the antiderivative of e to the x would also be e to the x, but we need to include that plus c. And these are going to be the two most important formulas that we introduce in this section. In fact, a good study habit I would recommend is keeping a running sheet of paper filled with the most important formulas and properties that we have encountered. And I would most certainly, add these formulas to your list. This formula with differentiating the exponential in general is something that we are going to revisit and determine precisely what this number f prime of 0 will be. But for now, let's go ahead and go through a few quick reminders of differentiation and integration formulas, and then practice some examples because we now have some new formulas to work with that we haven't had in the past. So in terms of differentiation formulas, we should be extremely quick and efficient with the product rule, quotient rule, chain rule. We've previously written down the chain rule, so let's go ahead and remind ourselves. The product rule tells us the derivative of f times g is the derivative of the first times the second plus the first times the derivative of the second. The quotient rule tells us that the derivative of f over g is low d high minus high d low, all divided by low squared. And then another reminder of U substitution, which I know we've encountered and we've used, but this is really a technique that needs to be second nature for us. When we are integrating a function of this form, if we let u be equal to g of x, then du will be g prime x dx. And we can take a possibly difficult looking integral involving all x and write it as a hopefully simpler, easier to evaluate integral involving all u's. Once you integrate, you make sure to resubstitute. And with these reminders, you see two differentiations waiting for us at the bottom of the page. I would like you all to pause your video, give yourself maybe 2, possibly 3 minutes, and differentiate these two functions. So now that you've paused the video and you've gone through some work, let's summarize. To differentiate e to the 2x, we will use the chain rule. The chain rule tells us that we take the derivative of the outside function, e, we evaluate it at the inside function, 2x, and we multiply it by the derivative of the inside function. Note a couple generalizations of this that we will encounter frequently. If you had e to the kx, where k is any non-zero constant, the same pattern would hold. You take the derivative of the outside, evaluate it at the inside, multiplied by the derivative of the inside. Or even more generally, you could have something like the derivative of e raised to a function f of x. So you differentiate the outside, evaluate at the inside, and multiply by the derivative of the inside. For the second example, we are going to need to begin with the product rule. You have one function e to the x times a second function cosine of x squared. So we take the derivative of the first, and I'm just going to write out precisely what the product rule tells us, times the second, plus the first times the derivative of the second. The derivative of e to the x is simply e to the x. And to differentiate cosine of x squared, this is where we once again need a chain rule. You have an outside function cosine, an inside function x squared. So you take the derivative of the outside function minus sine, evaluate it at the inside function, and by the chain rule you multiply by the derivative of the inside function. And once we get it to this point where we've evaluated all of the derivatives, I am more than okay with leaving it in this form. And if you're someone who likes to fully simplify, that's perfectly fine, and we will simplify when we need to simplify. But for now, I'm going to try to keep our focus on the calculus portion of the problem. Let's look at one more additional example. So back to this commonly encountered problem. Find the equation of the tangent line to some curve at a value. Without doing any work for this particular problem, we can immediately write down the form of that tangent line. It has slope given by f prime of 0, and it goes through the point 0, comma, f of 0. And immediately we see that we need to determine two values. What is the number f of 0? What is the number f prime of 0? And that guides our work. For the function e to the tangent of x, we can immediately substitute in 0, and we would have e to the tangent of 0. Tangent of 0 is 0. E to the 0 is 1. So we've determined the first of the two values that we need. F prime x, this fits the form we discussed on the previous page. It's e to a function. The chain rule tells us we differentiate the outside function, evaluate at the inside function, and then multiply by the derivative of the inside function. The slope of our tangent line is then f prime of 0. So e to the tangent 0 times secant squared of 0. And when it comes to simplifying, this is a scenario where I definitely need you to take it further. Whenever you have the trig functions evaluated at common angles, so think 0, pi over 6, pi over 4, pi over 3, pi over 2, common multiples around the unit circle, you always need to give those values. In this case, we've already said tangent of 0 is 0, and secant of 0 is 1. So this is 1 times 1, which is 1. And we can substitute these values into the left, and we have y is equal to 1 times x minus 0 plus 1. And you could leave it in that form. Or you could write this as y equals x plus 1. So that finishes our current discussion. What remains is to continue practicing with these two new formulas related to differentiating and integrating e to the x. So stay tuned and take care.